All right, well, let's go ahead and fire this off. So, good morning, good afternoon, good evening, and welcome to the Rise Up podcast. We are back after a brief hiatus, and we're going to get right into it. So, we've talked a little bit before about the unified namespace. We've talked about manufacturing data hubs and things like the data broker, which is a lot of how do we get data moved around? How do we connect all these various systems. We talk about this connect, collect, store, analyze, visualize, and a good chunk of that's just really been on that connecting and collecting. But once you get into storage, it sort of seems to be a little bit of hand waving, and we just say, oh, you're just going to go put it in some kind of database, and then when you need it back for some kind of retrieval, you just go ahead and get that. But as we talk about these types of things, we realize that there's a lot of different ways to store data and a lot of different data structures. And really, as I like to say, your backend matters. And joining us again today is a previous guest on the Rise Up podcast joined by Andy German. So, Andy, if you could just take a quick moment, and even though people are very familiar with who you are, we might have some new people. Please take a moment to introduce yourself to our guests.
Yeah, sure. I'll be quick. No one's that interested, I don't think. But been with Rhize for about 3.5 years now. Got a long history in software development and software generally in the manufacturing space. Probably 10 to 15 years in a technical sort of software engineering role, and probably about the last 10 years in kind of leadership and architecture roles and that kind of thing. So I'm customer facing. I like getting right in front of the customer and solving the actual problems. And I get exposed to a lot of the technology as well in doing that. So that's me.
A lot have been there and done that. So deep manufacturing knowledge, especially around the collecting and storing of data. So, when I'm talking to customers, I generally refer to, and I've heard others do the same, there are really two different types of data that you have in a manufacturing environment. There's your time series data, that's your telemetry data, it's time value, quality, and that gets stored in some kind of historian or time series database. And then we have this event database, and that's where we're putting all of our events. Could you talk a little bit more about some of the nuance that's there? I know we're going to be talking in a future episode about the difference between a process of storing in a time series database, but can you put a little more meat around what do we mean by the differences between a time series data and an event data?
Okay. Right. Yeah, I think you mentioned in there about time series data fundamentally being TVQ. I think that's the starting point for working with time series data, and that matches up quite well, really, with how do I historize the process values that are coming from these PLCs effectively. So as a kind of a small area within manufacturing, a small sort of slice of the manufacturing domain, matching time series databases and time series concepts with data that's streaming out of the process at level 0 or level 1 sort of makes sense. And you could view these discrete values that are coming out of the process. You could view those as events. Tiny little events, but again, they've got some meaning and not that much context. But we also, if we kind of look at a slightly broader scope in manufacturing and look at what else we've got that's event driven, it's not just process values. There are more complex things going on, particularly during execution stage in a manufacturing environment, where these objects that are being published, these events or these things that are happening down on the line and in planning and in other areas, they're more complex. These objects have got structure. They've got many attributes. They might have relationships with other entities. They might have child objects, or they might have other sort of relationships to hierarchies within your domain and that kind of thing. And so, when you start to think about these more complex objects, they've definitely got a time component, but it starts to become difficult to really think about storing those in a time series database, because the time series database doesn't really lend itself well to these complex sort of data structures. And so we'd look at another way of doing that. And there are other databases out there that would allow you to sort of store complex data structures. And a document storage system, for example, is an obvious one that comes to mind, where you can sort of dump complex documents into MongoDB, for example, and that gives you a way to sort of persist those kind of events. But again, when data is non-trivial, when data needs to be meaningful, it tends to grow relationships. And then when data tends to grow relationships to other entities, that's when a document storage system like Mongo would sort of tend to fall down. And then if you're trying to store that kind of data in a relational database, that makes sense. But again, when the relationships become very complicated, storing the data might be possible. But then when it comes to querying the data with complex relationships out of the relational database, that becomes quite cumbersome and not very convenient. So then we move over to graph, and maybe there are other databases that we might want to use for different kinds of databases. So we've got vector databases and that kind of thing. So I think it depends on the structures of the data and how you want to place it and how you want to consume it. I think that's part of what we need to consider.
Okay, so when we talked about time series and event data, there's a lot more that goes into just the event data, because as we're going to get into that back end, and that structure really depends on what's the type of event, what's the relationship, all the events, what does all this stuff look like. So as we were getting ready for this, there's sort of an evolution of the production and the creation of data in a manufacturing environment, and you refer to these as the pillars. So if I understand right, we start with the definition, then we get into the demand, and then finally there's the result. So let's unpack that a little bit. What do you mean by this data? These flavors or these pillars of manufacturing data.
Okay, so it can be quite difficult to talk about this stuff in very general terms, because you end up talking in a really abstract way. About time series or graph, and it all becomes very technological and very, very technical. So there's this sort of model that I use with my customers to try and sort of bring to life the differences between this data as the data lifecycle unfolds within the factory. So making a start on these three pillars, the first one here is definition, and this data is what people would often refer to as master data. I want to avoid using that terminology, and I'll come back to that. But definition data describes what the factory could do. So it describes the materials, the people, the equipment, the physical assets, the operations definitions, that kind of thing. It's all of the static data that's not going to change that often. And really is a representation of what is a very complex thing, the factory. And once you've got that definition in place, in a factory, then the next thing that you would do, or the next thing that an organization would want to do, would be to create demand on the factory. So creating demand on the factory really means understanding the sales forecast, the actual sales orders that we've got in. And somebody in production planning generally will create demand on the factory based on the demand that's coming in from the customers, or the expected demand. So that's orders, and whether you call them works orders or production orders or job orders and that kind of thing, we've got this activity in the factory that defines what the factory will do. And then the moment that an order's been dispatched into the factory and we start working on it, then we start getting the events. We start getting sort of real-time events coming through from the factory, which describe what the factory did do, what the factory has made. So I've got a sort of a summary of that there up on the screen. We've got definition, which is what the factory could do. Demand is what the factory will do, and result is what the factory sort of did do. Moving further from that, or further into the detail here, what this gives us in the domain of definition, we've got some really complicated object models and data structures like ISO 95, where we've got materials, and we've probably got a material taxonomy or a material class taxonomy, and then we'll probably have a lot of definitions for the different raw materials, the different finished goods, how all of those interrelate. Same goes for the equipment. We probably have equipment classes and equipment hierarchies. Then we've got the operations definitions, the work masters. All of this stuff, starts off as a hierarchy of sort of operations definitions and segments, and then we also have relationships between entities that allow us to sort of route materials in different ways for different jobs and that kind of thing. So it becomes a very complicated object model with a lot of relationships, and it's characterized really, these sort of things that I've got down at the bottom in yellow. It's characterized by complex data structures, as I've said. It's very slow moving, so it's not changing that often. You're not adding new entities to your definition model. We're not adding lots and lots of new equipment every day, not normally, and not lots of materials or people every day. Normally, once it's built up, the ebb and flow of definition data is a kind of an ongoing curation of that data, and it's long-lived as well. Unless your factory changes radically, the data entities in place will probably just churn on versions rather than sort of radical change. And this stuff's really foundational for later context, which we'll touch on, and also for business logic, so driving business logic. So you might have state machines in that definition that dictate that if you've closed an order, you can't reopen it again, or if you've got an order that's in quarantine, then some quality steps need to take place before it can come back out of quarantine. Normally, these definitions are coded up in a certain way. And then
it sounds like the definitions are sort of the what's and the how. And once you've got established what the what and the how is, then it's like, okay, now let's move on to the when.
Exactly that.
Yeah. Okay.
Yeah, exactly that. So now that we know what our factory can do, then we place demand on it, and that's just, it's simpler. It's scheduling and it's creation, dispatching of orders. So from a data structure point of view, it's much simpler. But actually, from a business logic point of view, it can be one of the most complex parts of a manufacturing organization. The whole deciding what to schedule on what machine when to really fit that demand, and the complexity that leaks back up into the supply chain is not something to be underestimated. Anybody that's been to sort of an automotive plant will understand just how sophisticated the planning gets in those kind of places. But it is the data structures that you're working with are not as complicated as the ones in definition. We've got hourly to daily sort of data churn, when new orders are being created constantly every hour and modified constantly every hour, and then going out of fashion after only a few days once an order's been completed. Often, with the people that are working with this data are sort of moving on to new things, and then these orders sort of become the subject of later analysis, if you like. So the demand data, the orders, are an enabler for business context, because if you can tie some piece of data that's sort of floating, some process value, or some material, like if you can tie that back to an order number, often that order number is the gateway to all the context that you've got on the left-hand side. So your order number, sort of in the middle, is what really ties the context back to this sort of complex sort of definition model that you'll probably have in a graph. So yeah, that's demand then David. That's the when, and then the final part is what the factory did do, and I've put that in past tense deliberately there. I've not said what the factory is doing. It's what the factory did do, and this is kind of one of the fundamentals of event-driven architectures, is that when you receive an event, it's something that has happened very recently, but it isn't something that's about to happen or needs to happen. The result is about an event that's recorded something that's happened on the shop floor, and again, we get these results. The data structures are quite simple, but they come in through different channels. So this is the results generally are characterized by sort of high frequency data in motion. So this is the stuff that's coming through from your broker, and it will be mixed with stuff that's coming through from operators transitioning orders to be running, or recording quantities of materials, or scanning barcodes, that kind of thing. So we'll have these sort of more complex or human-driven events sat alongside machine-driven events and telemetry and that kind of thing. So, you know, sort of for the three, we've got really different personalities of data across those sort of three domains. You know, on the left-hand side, we've got, you know, on definition, we've got this ongoing curation of data. And then in demand, we've got this sort of daily or hourly sort of, most often sort of manual manipulation and creation of orders to create the demand on the factory. And then in results, we've got high-speed, event-driven data streaming in from brokers or OPC servers, or from PLCs or other data channels, which we've got to deal with. I mean, the idea that the trick is with this is to, how do we combine these sort of three areas so that when we're interested in data from one of these domains, we can mix that with data that's sort of already exists in one of the other domains. And obviously, this model, like all models, you know, no model is correct, but some models are useful. This is kind of, if you look at the contrast that I'm sort of trying to paint here, there is it is useful to try and think about the way that this data behaves differently in different environments, but there's a huge overlap here.
Oh, absolutely. Yeah, I mean, it seems like, you know, when I first started with the conversation of time series and event, it's, well, yeah, there's events, but there's also a lot of other data that goes into manufacturing of it. And I don't even know how I would characterize all this. So, you know, we've spent some time talking about the pillars, you know, the definition, the demand, and the result. But, and I think we've gotten a little bit into the life cycle of the data, which is really, how does, you know, where does data start and where does that data end up?
Yeah.
Have we already talked about this, Andy, or can we just move on past that data lifecycle point?
Oh, let's touch on it. Again, you know, it's a sort of generic way of thinking about data. So that this data lifecycle model here, we've got sort of creation and collection of data, the transmission of data. So creation and collection, you know, where are we sourcing that data from? Is it from PLCs, barcode scanners, users, scales, that kind of thing? Or is it from another MES system, or is it from SAP, or is it coming through from a master data file? You know, we've got a lot of that, you know, a lot of consideration to make for creation and collection. And then transmission tends to be a technical thing. You know, how are we actually getting the data from one place to another? Are we querying? Are we publishing? You know, what are the technical aspects? And then storage, we generally store it in a database, but you know, we could have data sat in sort of Kafka streams, or you know, we could be just sort of leaving data in a broker. And processing and transformation, that's a key part of it. What we do at Rhize is the processing and transformation of data, not just to grab context from the graph, but also to position data into different sort of different databases for different consumption later, for analysis, sharing, and utilization, which are the other parts of the data lifecycle. And then we've got archiving and retention and disposal of data, which are sometimes not really considered when you're sort of architecting the happy path, but important considerations when you're sort of looking at the broad sort of cost of ownership of a you know, a heavyweight data architecture. So yeah, the data lifecycle. So I think what sometimes happens, if you're talking about a specific area of technology or a specific set of use cases, you can tend to focus on just one bit. So you'll get sort of data scientists will be thinking more about processing and transformation, or storage, processing and transformation into analysis and sharing, whereas OT people are really focused on creation and collection and transmission. maybe IT admins, maybe they're focused on archiving and retention and disposal of data and that kind of thing. But I think it's important to just keep in view that there's quite a broad scope to data management. And so that's the data life cycle, and I think it's relevant when you're mixing database types and mixing the location of data as well. So some of it's in cloud, some of it's on-prem. We've got data lakes and data warehouses and all that kind of thing. This stuff becomes important to manage explicitly at a governance level, a group IT level.
Yeah, so we've gone a long way from just time series and events to, well, there's pillars of that data. There's the demand, there's the definition, there's the result, and well, now we also have a life cycle. All of this data that you're going to collect and store and analyze, you're also going to have different places for it of when it's created and how it gets used, and then eventually where do we park it. So we talked a little. We haven't even really gotten to the gist of it. And I think now it's a great time to do it. And you alluded to it earlier. Of there's all these different data structures that can actually exist for it. So not only do we have the pillars and the life cycle, but there's different data sets. So let's really get into understanding. What are these different types of we'll just call them generically databases that can be used, and how should they really be be utilized to maximize what it is we're trying to do?
Yeah, sure. Okay. This is like you say, the meat of it, the bit that we wanted to get to. Databases. I'll pull up a diagram here on my screen and sort of work through that a little bit. We've got discrete values that come up from the process, from PLCs and that kind of thing, and it would probably land in some kind of OPC server or MQTT broker or some system that can sort of provide these discrete values, and that's the starting point. Often when we're sort of architecting systems, we're kind of assuming that the stuff that's coming up from the PLC is getting sort of transformed into a format that can be consumed by a tag system. So we've got discrete values. We've got as you described it earlier, David, the TVQ thing. It's raw data. There are no relationships in place, generally speaking. So we've only got the discrete objects that we're dealing with. And we've got sort of high frequency data streams. So you might have temperature values or valve open close values coming in at millisecond sort of resolution and that kind of thing. So there are not many relationships there are no relationships at that level, and you might not even have much context either. So you might have an ID indicating which equipment this is from, but certainly most of the time you wouldn't have an order number, and you wouldn't necessarily have a material sort of number associated with a value. You probably won't even get a unit of measure. You'll just get these sort of raw values. So yeah, that's a tag system. The data doesn't really become meaningful until you start creating relationships. And the next sort of area of interest really is, how do you represent complex relationships? And really, the answer to that, really in sort of modern database sort of design, it's accepted really that graph databases are often the most appropriate way of representing sort of complex object models. So, an example of a complex object model is ISO 95, particularly the stuff that we've talked about on the definition side. So we've got complex relationships, we've got recursion, we've got the need to sort of traverse many joins. We might have the requirement to sort of scale horizontally and that kind of thing. So with a graph database lends itself to that kind of thing, and access technologies like GraphQL again make it convenient to access a graph database. in the past, or up until, well, let me give you the example of ISO 95. I think ISO 95 is a good example of an ontology of a very, very complex object model. It's been really very difficult to implement using relational database technology in the past, because of this idea of object relational impedance mismatch, which is jargon and it's a right mouthful. But what we're actually talking about there is that when we've got complex nested objects with relationships attached to them, it can be quite hard to translate that representation out into a relational database. And that this has been a kind of a bugbear of object-oriented software engineers for the last 25 years, however long we've been doing that. It's been that they can really express themselves within their own software object-oriented software environment. But when it comes to persisting or querying the data back out of the database, there's always this object relational translation layer that really gets in the way. And I think in the past, that problem has made it very difficult and impractical to implement complex object models, because relational databases have been the only outlet for doing that. But we're here with graph databases now, and it suddenly that problem goes away. It brings with it other challenges and that kind of thing, but your ability to express yourself and really place the data and relate it to each other in a way that makes sense for the problem that you're solving, the manufacturing domain. It really, that your ability to do that comes to life with a graph database. And that's why often we use graph databases, and that's why, particularly in the definition side of ISO 95, that sort of comes into its own. I've touched on relational databases, and I'm breaking this down into sort of two categories. There could be a third category actually, but I'm breaking this down into sort of row-oriented data, which is your traditional SQL Server OLTP transactional database, and column-oriented data, which is lends itself more to analytics. So for the row-oriented data, this is what we used to see, and it lends itself really well to the demand, the bit in the middle, for the three pillars of manufacturing. The idea that you're working with an order as an entity, and you're dealing with groups of orders and that kind of thing, kind of lends itself to row-oriented data structures, row-oriented queries, and that kind of thing. In fact, the reason it's been so popular for so long, it's just so flexible. The row-oriented relational database technology, really flexible. So low query latency for analytics, small data set for analytics is okay. We've got ACID compliance and bulletproof reliability, and your ability to delete and update records and frequently access records sort of lends itself to working with traditional sort of transaction processing and that kind of thing. Okay, so that's row-oriented data, and again, it lends itself to the transaction processing and what we'd normally see as sort of traditional IT systems. And then we've got very closely related, as I said, relational databases. Column-oriented data is another way of dealing with data that's got a slightly different query workload. So for transaction processing, as I said, records are king, or rows are king. In column-oriented data, the difference is that the way that the data is arranged on disk or in memory, let's stick with on disk for now, means that it is faster. The data structures on disk lend themselves to algorithms that are trying to do aggregation type stuff. So these are your OLAP databases, online analytics processing. So where you need low query latency, where you've got massive data sets, where you've got maybe some time series in there, where you need to do some compression, where you're working on large data sets and not necessarily on a record by record individual basis, then column-oriented data comes into its own. And the difference between row and column is just whereabouts on the disk the different elements are stored. So in row-oriented data, a record, the data all associated with an individual record would be kept together, and to traverse a lot of records would be resulting in a table scan, which can be quite expensive. Whereas in a column-oriented database, the data that lives together are the data that's related to a specific column. So if you've got a data set that contains a lot of numerical data, then the column for height or temperature, all that data will be stored together. It won't be scattered across the disk. So we've got this, when you're trying to do aggregation on a column, the way that row-oriented databases organize that data on a disk would be it would be fragmented and distributed more across the disk, and difficult for an algorithm to access and gather and bring that data together. Whereas a column-oriented database, there's an assumption that there's going to be an aggregation workload, and therefore the data is sort of oriented on the disk in a way that's convenient for algorithms that are trying to do that work. And this is why with a lot of time series databases, and I know Influx is one of the ones that uses a column-oriented data structure, because typically a time series database will be dealing with aggregations as a sort of first-class citizen. Time series takes it one stage further and adds a time component to the storage that it's using on the disk, so that when you're using time series databases, you would probably be doing things like interpolation, grouping by time elements, last observation carried forward queries, and other aggregations. So what you'd have with time series data is it will be optimized for doing that across time. So that's column oriented. You're going to say something then, David?
Yeah, I was just going to say, it sounds like a time series database that we've talked a little bit about is just a very specific instance of a column-oriented data. Is that correct?
Correct, yeah. And I think a lot of the data warehouses, Google BigQuery, there's certainly one option for using Google BigQuery is to have it as a column-oriented database. And they've not yet released time series, certainly not on general release, I don't think. They've not yet released some of these time series features, but they're going to catch up with that, if you know what I mean. So kind of time series could be viewed, maybe I might be wrong about this, but could be viewed as a kind of a subset of column-oriented databases.
Yeah, I think that's fair. All right, so now we have this document store. Tell me a little bit about that.
Document store, MongoDB being the sort of the most widely used example. So document store, we don't really use it at Rhize. I have used it in a past life. What a document store allows you to do is effectively store, let's take MongoDB, store JSON documents. So in a document store, you'd have the equivalent of tables would be, rather than containing rows, would contain documents. They would contain JSON documents. So in the case of MongoDB, it's a binary format, so I think it's BSON. So your document store allows for complex objects to be stored, but it doesn't allow for relationships, not really, between documents or between documents in different parts of the system. So, as I said earlier, when data starts to become, or when you need data to start to become meaningful, or when you want to derive meaning from data, often relationships start to grow. And this is a weakness of document store systems, is that they're very fast on ingest and fast to query. But when it comes to sort of building relationships between different objects, the method is embedding. If you want quick access to something that's related to a particular document that you're dealing with and it lives in another document, rather than create a relationship and traverse that relationship through a query in a document database. Generally speaking, what you would do is embed and therefore duplicate data inside that document, so that you've got the data sort of living alongside it. So document stores kind of you can end up with a lot of duplication, and you can end up with a lot of orchestration of queries and stitching of data back together in the application layer. So there are kind of a few niche use cases for document store. But I think what a lot of people, if they overuse document stores, what can end up happening is that the application layer ends up with a kind of a referential integrity layer having to be built to make sure that if you delete a parent document, it's related to something else, then you go off and delete the child documents from other places, or you end up with logic in the application layer that actually synthesizes relationships between documents by sort of scanning full tables and making matching foreign and primary keys across the two tables. So you end up getting a kind of a quick win early on because it's a schemaless database, so you can kind of just dump data in there. But your quick win results in quite a lot of technical debt that then needs paying back in the ways I've described a little bit later. So
no good deed goes unpunished.
Well, sometimes you get there fast, right, and it delivers value, but then you've got to pay back at some stage. There's your technical debt. It happens everywhere. It catches you out with Mongo for sure.
All right, perfect. So we've talked about the different pillars. We've talked about there's actually there's the evolution or the life cycle of it. Now we've talked about really in a manufacturing environment we have sort of that tag data, discrete data. We have the graph database that builds relationships in. We have row oriented for some transactional data. We have the column oriented for more of the analytic data. The time series being a very specific or a subset of that. And finally, there's just the generic document store, I would say. So can you start bringing this back and, what does this data structure look like and what does it mean and within the context of, let's just start with the pillars of, we have the definition, we have the demand, we have the result. How would you utilize these different data sets for capturing this kind of information so you could maximize the value of all that data that you're collecting?
Yeah, okay. Well, I've sort of talked about a couple of models there. And as I said, all models are wrong, some are useful. I'll try and combine these models now, the ones that are just presented, to sort of try and bring to life why we're talking about them in the first place. Again, there's a diagram on screen there that sort of brings the two together, and it just sort of exposes a way of thinking about how these things come together. So definition data could do what the factory could do, demand data what the factory will do, and result data what the factory did do. We've got a progression there between those three sort of areas. The definition data, it's complex objects, it's relationships, it lends itself to graph databases, very much lends itself to graph databases. And that's how we're able to sort of expose ISO 95 as a persistence ontology within the Rhize platform, is using a graph, and we're able to sort of represent those relationships there. It's hard to do that with row-oriented database and column-oriented databases. You end up with loads of joins and really complex queries and quite a lot of frustration. So you end up watering down your complex object model so that it's a poorer representation than could be of your manufacturing environment. You don't have that constraint with the graph database. So that's where we, our definition data, we put that into graph. Complex object store. The demand data, again, we've said it lends itself well to row-oriented data structures, online transaction processes, because it's orders and schedules. Within Rhize, we've got the graph database there ready. it works well with that kind of workload, with that kind of concept. So we tend to keep the demand data, the scheduling data, in the graph as well. But again, row-oriented data attached to that. What we're always doing at Rhize is we're never the full picture. We tend to use the different parts of our Swiss Army knife, depending on the circumstances. So we would often interface to a scheduling system or consume orders from SAP, for example, and that might be one use of the sort of the row-oriented data. Okay, so demand, yeah, we've got these orders, and we're managing these orders daily, hourly. As I said, it lends itself to the row-oriented data. But in Rhize, we've already got the graph database there available. It can cope with this workload quite well, and obviously we've got the data structures there available from ISO 95 to support that. So what we do a lot of within Rhize is to work with other systems. So we never normally the complete solution. We're normally sort of working with different tools on our Swiss Army knife to sort of pull together the integration to make a full solution. So we'll probably be working with SAP or some other ERP system to onboard data from order data. We might be working with a scheduling system. We might be deferring the scheduling tasks to another system because that functionality is sort of rich in that environment. People are used to it, or so we would tend to sort of work with what's available there, and often that's sort of that row-oriented data or SQL Server, effectively most of the time. And then if we talk about result data, this is the bit where it all comes together actually. And when people talk about event-driven architectures and event-driven manufacturing and that kind of thing, it's this result data, what actually happens on the shop floor, that's really the bit where the value is, where the value of the data is. This is the bit that people want to analyse. They want to understand what happened in the factory and why and what it was related to. So this is the bit where it all comes together. And I've not mentioned discrete values so far, but discrete values will be a primary contributor to the result, part of our sort of our three pillars. So we've got these discrete values that come in at very high frequency, and we would normally land that data. It would come through a broker generally speaking, and we would probably land that data for the most part into a time series database, a column-oriented sort of time series database. On the way through, part of the the life cycle, the data life cycle is this idea that we transform and contextualize. So as we receive these discrete values from a broker, we would tend to make associations with that data with the usual tools, primary keys and foreign keys that would be sort of queried and stored in the right place. But we'd grab context before we persist through into time series, and the context allows us to maintain and preserve the relationship between the data that's coming from the process, the discrete values, and the object model that was used to sort of define the factory. And same with the row-oriented data. If we've got links to, or we're able to query across the different databases to bring it all together, then that's the part where we can enable and facilitate contextualized analysis, or we can enable and facilitate the contextualization and pre-formatting and transformation of data as it comes into the result end of our data model, and post that off in the right format off to a data lake or some other some other persistence layer that would be used for the querying.
So it sounds like that, we've talked about the pillars of the data, and then when we get into the definition of it, we really want to put that in a graph or some sort of a very highly contextualized relationship. And the graph, the knowledge graph really lends itself well to that. And then of course, once we get into the demand, that can either be in a graph, or we can, traditionally use a row oriented data, and that's very common, and it lends itself very well. But where we get into the result, that's where we're going to see all of these different types of data sets being used. We're going to have the discrete values going to the time series data, and we talked about that's a subset or a specialized, a tab oriented, or excuse me, a column oriented database. But when we want to get into the analysis of that data, what type of analysis you want to do really is going to determine and define the type of data that you want to use. So if your analysis is a relationship of data, then using a graph, or a highly complex relationship, use the graph. If you want something that's more of a transaction, that's when we're going to want to start using more of the row oriented. But now if you need to start doing some kind of analysis, so when we get in, you mentioned BigQuery earlier, where we're going to do all kinds of analytics, that's where you get into that columnar piece, because it's going to lend itself well. Do I understand this correctly?
Yeah, you do, and the thing I want to reiterate is that there are no hard, fast rules about this. There isn't a kind of there's a rule. These are ideas that need to blend together. So yeah, the idea that if you know that you're going to be doing a lot of aggregation on massive data sets, then you're going to be going in the direction of column-oriented data. But if you know you're going to need to do sort of traverse a very complex graph structure for, I don't know, product genealogy or something like that, then graph might be it. If you need to represent very complex structures like an ontology, graph might be it. You've got this blend, and sometimes these things blend together. So your column-oriented data, the data that you want to push off into a data warehouse, you might want to you might want to push that off in the format of Parquet files, because that's what's important. But you might just want to break a few context items out from the graph and put them into those Parquet files, just to make later queries more convenient. So maybe some primary keys from your graph sort of object model will help you grab context later, if that's what your data scientists need to be able to do or want to be able to do. And actually making those decisions is a kind of a project by project, data model by data model sort of problem that really needs to be kind of, you've got two sides to the consideration. One, am I representing my data structures correctly and to the right fidelity? And then the second part is, what's my workload? How do I want to consume this data? And depending on those two, depends on how what emphasis you place on these considerations. But if you leave any of those out of the consideration, and if you leave graph out, or if you leave row out, if you leave time series out, or you leave out the other channels like the broker or whatever that means. If you leave any of them out, you leave yourself actually with probably not the right number of tools to solve the problem that you're likely to have in manufacturing, unless the problem's dead simple. And I think for large organizations with many factories and that kind of thing, the problems are never that simple, really.
And unfortunately, no, there's a lot of complexity that goes along with it. So I wanted to talk a little bit about just data models. I use the term semantic data model a lot, and I generally speak this in terms of, say, like an asset. So for people that know me, that's your motor model, that is your compressor model. That's something that's not just describing, these discrete bits of information. We'll just call them tags if you're familiar with like a PLC or a SCADA system. But we want to model it as an object. It even could be, say, a mixing tank that has a mixer, it has a level. There's a lot of things that describe what that is, and that becomes that semantic data model. But then there's also the technical model of what does this overall structure of the data look like. So, as we start collecting all this data and think about, here are the pillars of data, there's the life cycle of the data, here's the different data structures. Well, we do need to start exchanging this data a little bit. So can you talk a little bit about, these both, let's expand a little bit on the semantic model as well. Let's talk a little bit about the technical model there as well. And what does this mean in the context of the storage of the data?
Okay. Yeah. So semantics being meaning, I suppose. When you've got again that landscape, large organisations with many factories and many, you might have MES and ERP and LIMS and all kinds of other systems and sort of siloed data stores in a lot of different places. You can. There's always in IT. There's always the technological imperative that you've got to create interoperability between systems from a technical point of view. If there's no pipe between the systems, if there's no technical way to integrate, then it's kind of pointless. And this is why we've got, this is why we have REST interfaces and why we have brokers and HTTP, and why we have databases and query languages and data structures and data formats, why we've got JSON and HTML and XML and all of these sort of technical, all these technologies that facilitate and enable interoperability at a technical level. But the bit that's just as important, but kind of gets missed a lot, is this idea of semantic interoperability. So when concepts that are shared by systems, necessarily shared by systems, like your equipment model, that's the best example of a structure that's shared by MES, by ERP, by LIMS, by other systems. They all really need to be talking a common language when they're referring to these things that are being shared. Like I said, the equipment model's the first thing that sort of springs to mind. And when systems do it differently, when semantically systems view equipment and physical assets in different ways, and they represent those structures in different ways, it can really you might have the technical interop in place so that, one system can call a REST API on another system. You might have that bit in place. But actually, if the two systems have got a different semantic representation of the thing that they're trying to exchange on, then an awful lot of technical work actually then has to take place at a translation layer to try and make the conversion between the two, the two systems. So, and it's like, if you've got an MES and ERP and some other system there, you might have orders, you might have works orders, or you might have production orders or job orders. They don't always mean the same thing. So, an important part of integration in a complex landscape is to somehow bring together this semantic interoperability, so that things can exchange information in a consistent way. And that's the bit that's hard. That's the bit that's really hard, I think. The way, and it's becoming more of a topic at the moment, or a more important topic, or something that's being talked about more at the moment, just because of this sort of rise of large language models and this idea that we can use retrieval augmented generation to sort of ask questions of our data and use large language models to sort of navigate the data that we've got. And a kind of a fundamental starting point to be able to do that kind of stuff. If you want that ambition to be able to use sort of large language models and AI generally, and use them specifically on your data set, the thing that's getting in the way is not technical interop and not technology interop. It's this semantic interoperability where the LLM's not got a chance of actually interpreting all of this data. And in order to sort of create this semantic interop, you need an ontology. Maybe you need an ontology. It's kind of there are different schools of thought here, but an ontology that describes a domain in detail and the relationships between the objects in detail, is a starting point for that interop. Now, that when you talk about the sort of the semantic layer in a UNS, that's a great example of where a very small part of ISO 95 has been encoded into what is probably, in most practical terms, a topic structure, and they've used a sort of enterprise site area line model to sort of organize the equipment hierarchy into a sort of a composition hierarchy of equipment. That agreement between systems, that agreement between the guys that are building the UNSs and the guys that are going to consume the UNSs, that agreement on that semantic framework is a big part of the enablement of a UNS. If you were going to choose those topic names, those topic structures at random, it wouldn't be a UNS, because the consuming the data from the UNS would be inconsistent, depending on what decisions people have made. So the decision to go with ISO 95 for that part has enabled a kind of a semantic interoperability, but it doesn't just stop at sort of the equipment hierarchy. If you're going to get a true value from the data, it needs to go further than the equipment hierarchy. It needs to, we need to visit materials and people and recipes and routings and all that other stuff. And where you put that, that's the debate. That's the debate for architects and engineers. Is, do you pick one of the systems in your landscape to be the representation? Do you choose or build a new ontology to make this sort of universal representation? And that's kind of it's a big problem. I've no solution for it, but I think it's it's the kind of the interesting thing that's going on at the moment is, do we really need to arrive at a sort of universal sort of semantic interoperability for manufacturing? And if we do, how do we go about doing that? And I think maybe ISO 95's got something to do with that. Maybe there are other ontologies that could be reused. But I think that's the thing that's coming through for me at the moment, and I can really see that being a problem as these technology interop problems start to get resolved more readily.
Yeah, as we've evolved in this so-called digital transformation, there's a lot of new ways and new approaches to the types of things we're doing. I don't think we've arrived on what that looks like, but certainly there's a lot of very smart people that are coming together to let's see if we can't figure out and what is this going to look like long term. And I suspect we'll probably land on something.
Yeah.
And then just about as soon as we have all decided, yeah, this is what we're going to do, then something else is going to occur, and then we'll be right back at it. So I suspect we're going to be iterating for a little while here. So, we've talked a little bit about, the pillars of the data. We've talked about the data lifecycle. We've talked about the different types of data sets and how they can be used. And even we've talked about, the semantic interoperability, these semantic models. You say we want to make sure that technically exchanging data, that's the easy part. Semantically, let's make sure that, what it is that we're talking about, we can get all our information around. So can you kind of bring everything together? Let's just, what does this look like? Let's pull back a little bit and just start looking at what does this look like long-term for everything? Can you tie this all up for us, Andy?
Oh, yeah, that's a big ask, actually, that, David.
That's right.
Yeah. I think it's in the past. If I look back on 15 years ago, it was the options, the architecture options, particularly if you're using other people's technologies. And I've always been lucky enough to sort of work in a product environment where we sort of building our own technologies. But if you're using other people's technologies and trying to stitch them together, the solution options have been very one-dimensional. So you use the vendor's data model and their extensibility model and their programming languages that they provide, and the options for integration aren't that great. So there's kind of this vendor lock-in idea and prefabricated architectures. I think we're coming through that actually, and people are able to take a sort of a composition approach to system design, where they can they've got more choices. They can choose to use different kinds of databases, and they can choose to use different sort of types of transport technology, and sort of so that and the technical interop between those elements again is maturing, and we've come through. So because we've got more choice, there needs to be a bit more kind of there needs to be more sort of mental models, if you like, of how to approach the different situations with these options that we've got. So if you're composing an architecture, because you can use a lot of different kinds of systems and a lot of different kinds of databases, that's when the problem of semantic interoperability starts to come in, because you're no longer just sort of using the data. You're using what you've got available. You've got choices to make around that. So I think as the sort of manufacturing architecture landscape evolves, people are going to be looking to mix the different database types, the different sort of transport technologies that are available. Maybe taking off-the-shelf products for implementing certain parts of functionality, maybe implementing, a full MES and a full ERP in the classical sense, but actually complementing this with a composition model around how they extract and transform and consume that data using sort of different technologies. And as soon as you break away from that kind of vendor-centric approach and take a more sort of democratized approach to the way that you're sort of solving these problems, that's when you're going to need sort of to start thinking about ontologies, and that's when ontologies like ISO 95 sort of come into their own, and the consideration that how do you adopt ISO 95? Can you force that into the MES vendor? Or do you need to create some sort of middleware that allows you to sort of act as a sort of almost not a single version of the truth for the data, but maybe a single version of the truth for the semantics? And how does that work? So I don't know whether I've brought it together. I've certainly named a number of very difficult problems for you there, David.
No, absolutely. There's a lot to think about here, and so if we go back to the very beginning, and I've talked about it's, and I'll reference this again, there was the Timeseries database, there was the event database. Well, what we've really learned here is that, there's a lot more to both of those events there. So we have that pillars where you're going to have your definition. You're going to have your demand. You're going to have your result. There is the life cycle of where does all that live and how does it live and how it moves its way through. There are different data structures that you want to use for those different pillars. And of course, bringing it all together, you also want to ensure that you're not only utilizing the right database, that's the right tool for the job, but we want to ensure that we're also exchanging all that data so it's not just technically interoperable, but we also want to maintain some semantic interoperability. So we've definitely come a long way from the time series and the event to there's a lot of things that go into it. The good news is that there's a lot more systems that will talk to each other. We want to think about exchanging data in a semantic interoperability way, and ensure that we also park the data and store that data and persist that data in the right sort of data structure, so that when we want to analyze it, when we want to use it, we're going to be able to maximize the ability. So does that seem to kind of conclude where it is that we've landed on this?
I think that rounds it off quite nicely. The only thing to add really is that the only thing you can be sure of is just kind of a long sequence of problems stretching off into the future.
Absolutely.
But
sometimes
this is what we're in.
Yeah, but as they say in programming, when you get a different error code, that's kind of that's an exciting day. That's right. That's progress. Anything else you want to add, Andy, before we sign off?
I think I've talked too much, actually, David. No, I think that's all good for now.
All right, perfect. Well, thank you for joining us, and thank you everybody for being here for the Rhize Up podcast. As I think we've really dissected why the back end of your data structure matters. And we'll look forward to seeing you on future episodes of the Rhize Up podcast.